Hi everyone, welcome back. This is the video. I wish I watched this video when I started to learn about AI. This is part 1, explain-01, and let's just get started. Oh, the URL is right there on the screen. github.com dev0 simple llama 3.x. Now that we've gotten familiarized with basic calculus, we can jump right into neural networks. So in this part, in explain-01, I'm going to talk about the key invention, and it is such a simple invention. So what I'm going to talk about here in this part is the one crucial genius idea that some very smart people about maybe 56 years ago came up with, that literally paved the ground for the explosion of AI in the late 2010s and ongoing now. Neural networks is basically implemented in terms of basic math. Add and multiply make up about the bulk of, maybe it's about 60% of the electricity that's consumed by the GPU. However, we're not going to be dealing with individual numbers or scalars. We're going to be doing math in larger units of numbers called matrices and vectors. So let's do a quick diversion. So what is a matrix? You can just think of it as a, for the lack of a better word, a box of numbers, a 2D box of numbers. And it has a specific number of rows and columns. As an example of a 1D matrix is called a vector. And this right here is a 3D vector. It has 3 numbers in it. One for x, y, and z. So there are multiple things you can do with matrices and vectors. One of them is the dot product. Let's go with that now. You can think of it as a element-wise multiply add of 2 vectors or matrices of the same shape. The dot product results in a scalar, basically a zero-dimensional vector or just a single number without a box. For example, if you have this vectors 0.1, 0.2, 0.3 and the vector 3, 2, 1, if you do the dot product between them, you get back the value 1. Okay? And the matrix times vector. If the matrix has some number of rows and columns, and the vector has the same number of rows as the matrix has columns. In other words, if matrix has A rows and B columns, and the vector has B rows, then the resulting vector has A rows and 1 column. Take a look. Think of it as rotating the vector or tipping the vector sideways like this so that it is lying down. And then you line it up with each row of the left-hand matrix. And then you just do a piecewise multiply add, and then you get the resulting vector. And here's how you do a matrix times matrix. Just as an aside, in Python, the official operator symbol for matrix multiplication is the @ sign. Okay, but we'll talk about that later. So if the left matrix has A rows and B columns, and the right matrix has B rows and C columns, then the resulting matrix has A rows and C columns. Basically, the inner dimensions, the B, drop out. And you can think of the matrix multiply as basically a sequence of matrix times vector, where each vector is the columns of the right-hand side. So basically, we're taking this column and doing a matrix times vector with this matrix. And then you get this column, and then you take this column, do a matrix times vector with this matrix, and you get this resulting column. Okay. So for neural networks and artificial intelligence, you can think of the matrix as just a configuration of a bunch of neurons. And the vector, in this case, you can think of it as the inputs to the neurons. So are we done? It's like, oh, well, now we can do. We have a matrix times vector, and then we just we take a vector and you multiply to the matrix, and then bada bing, Bob's your uncle. The answer is not quite. So this is the crucial invention that is again is such a genius idea, right? The differentiator the differentiator for genius ideas versus just merely good ideas is that the genius ideas are the simple ideas that no one else has thought of, right? And this was one of them. And this genius idea literally is what's known as an activation function. So it turns out that matrix times vector doesn't really give you anything. And the reason why is the derivative of matrix times vector is not going to give you any insight as to how to reconfigure the matrix so that the result is closer to what you want. Right? I mean, in other words, the slope towards zero is not going to give you an interesting solution. And this very simple, this crazy idea, right, that makes artificial intelligence work. Without this idea, artificial AI does not work at all. Right? And this simple idea is that we just need a source of nonlinearity. And the utterly crazy part of this is that this nonlinearity can be anything, almost anything. Like the exponentiation operators works sometimes. Hyperbolic tangent works sometimes. Things like ReLU that we just briefly covered also work sometimes. Right? That's literally it. Without this activation function, you can matrix multiply and onto the cows come home, but you will not be able to figure out how to tweak the weights meaning the values in the matrix so that the resulting matrix multiply gets you the answer that you want. Right? Okay, so let's diverge into some more vocabulary. A matrix, you can think of a matrix as a two-dimensional tensor. So what is a tensor? A tensor is, for the lack of a better word, a multi-dimensional number. Right? So matrices, regular 2D matrices, are tensors of rank 2. Regular vectors are tensors of rank 1. Okay? And the regular numbers, or scalars, you can think of it as tensors of rank 0. Okay? So an n-dimensional tensor of size k1, k2, k3, through k sub n, you can represent as an array of numbers of length, and you just multiply out the various k's, k1, k2, k3, through k sub n. Okay, and these numbers, the k1 through k sub n, is usually referred to as the shape of the tensor. Okay, so for example, a 2D matrix with row and columns, some number of rows and columns can be represented as an array of numbers of length r times c. A 1D matrix or a vector can be represented as just that vector, being basically an array of numbers of length of the vector. Single numbers can be represented as a single number, and let's say a 3D tensor of shape 3, 5, 4 can be represented as an array of numbers of length 3 times 4 times 5, which is 60. Okay. All right. So a couple of more things. So we covered matrix times vector. We covered matrix times matrix. The one additional note about a matrix is that there's another common operation for matrices. It's called the transpose operation. And you can think of the transpose as just literally flipping the matrix, just a 2D matrix, if you think about that, along the diagonal. Okay. So for example, if A is this shape, A transpose is this shape. Okay. If V is this shape, V transpose is this shape. So if you have a square matrix, the transpose still winds up being a square matrix, but the elements are flipped along the diagonal, as you can see. V01 used to be over here, but now it's down here. Okay, along the diagonal, the elements do not change. Okay, but above and below the diagonal, the elements do change. Okay, so if so, a tall rectangle becomes a flat rectangle when you transpose it. All right. So now the weird thing here is that even if A matrix multiply V, is legal, it's not necessarily the case that A transpose matrix multiply V transpose is legal. It's not guaranteed to be the case. But if you're paying attention, you can see that V transpose matrix multiply A transpose is legal, and it results in a legal shape. In this particular case, the shape is 2 rows and 3 columns. Okay, but but so in other words, A transpose is of shape 2 3. A was originally shape 3 2. V transpose is still 2 2, but and you have to remember that V transpose is not the same as V. And here is D transpose. Here, so this is the result of matrix multiply of A and V. I wrote it out right here. So, and here is D transpose, right? D is a 3 by 2. D transpose is a 2 by 3. So the question for you is V transpose matrix multiply A transpose equal to D transpose? The answer is actually yes. All right, so this concludes the very short explain-01. We'll be covering explain-02 in the next video. Okay, thank you very much.